Okay, distance versus time graphs. And when we have distance versus time graph, on the y component is distance and time is on the x component. All right, time is an independent variable, so it's always going to be on our x axis. All right, we have a bunch of different graphs. I'm going to go through and I'm going to describe what you're seeing. Okay, so if you have a distance versus time graph here and you have a straight line going down, it means a constant speed, negative direction. Now think of it this way. Let's say I am throwing a ball away from me. If I throw a ball away from me, the distance would be increasing, so it would be going upward. So if someone's throwing a ball to me, the ball's coming towards me. So the direction is negative. It's coming towards me. If it's going away from you, it's positive. That's why it's sloping down, because it's coming towards you. Because when it gets right here at 0, that's when it's at me. Okay? Next one is standing still. As time goes on, your distance is not changing. Okay? So what's your speed? 0, because you're not moving. The next one is a curved line going down. And in this case, it's just like this one up here, but it's not constant speed. It's decreasing velocity, or what we call a deceleration. Okay, it's slowing down. Okay. And then when you look at this one here, this is a decreasing velocity as well, but it's actually moving away from you. Okay, so this one's coming towards you, this one's moving away from you. So they both show decreasing speeds. Okay, this is going towards you, this is going away from you. And the slope of these graphs would be the velocity, how fast you're going. And then the last one is an upward curve that shows positive acceleration. This is like if you're standing on a bridge and you drop a ball, it's going to keep getting faster and faster and faster and covering a larger and larger distance. Okay, so the slope of these graphs will give you velocity. Velocity versus time graphs. This will have velocity on the y, will have time on the x. This shows a constant positive acceleration. All right, dropping a ball off a bridge is an example. Okay, it's going to keep going faster and faster and faster, and it's moving away from you. Constant speed means there's no acceleration, but it's still going with a certain speed. Okay, if the speed was 0, then it would be right on this line, but up here it would be whatever the speed is. Okay, now the interesting things about velocity versus time graph is that the slope will give you acceleration and the area under the curve. All right, so what's area? Length times width, or base times height. Okay, so if we measured this base times the height, all right, all of this area here, we could calculate how far it traveled in that amount of time. Okay, this being a triangle would be 1/2 base times height. Okay, rectangle, base times height. If you had multiple different things like a triangle with a rectangle and you had to add it all up, you just take each part separately and add them up. This is constant negative acceleration. All right, you're slowing down. Okay, and maybe you're coming to a stoplight. Okay, now all three of these are above the x-axis. Therefore, all three of them, you're moving away from your origin. If you were below your x-axis, then you would be moving backwards. Okay, like for instance this one, a ball being thrown up and falling down, or a child on a swing or a pendulum. Okay, for this one, if I was to throw a ball up into the air, this right here would be as fast as it's possibly going. And then it's going to slow down, slow down, slow down, slow down. It gets to here, and now it stops. And now it's going to fall down, getting faster and faster and faster until I catch it. All right. This area here and this area here would be the exact same amount because I throw the ball, goes up, comes down, I catch it. The total displacement, all right, is 0. Okay, so if I went up 3 meters this way and then it came down 3 meters, so the areas under both of these would be the same. What about a pendulum? I put BTB, so that would be from the bottom to the top to the bottom. So if you're pushing a kid on a swing, all right, right here at the bottom, he's going as fast as possible. He comes all the way up, he stops, and then he always comes back. And then when he's down at the bottom, he's going just as fast as he was this way if we neglect friction than he is going this way. Okay? So those are velocity versus time graphs. The slopes give you acceleration. The area under the curve gives you displacement or distance traveled. Acceleration versus time. The area under the curve will give you velocity. If we take the slope of these, it won't give us anything because the units would be meters per second cubed, and we don't know what that is. Okay, this would be constant positive acceleration, line on top. Zero acceleration, which would be constant speed or not moving, would be on the axes. And then underneath it, constant negative acceleration would be slowing down. Okay, and those are acceleration versus time things. So if I asked you to tell me a story of this graph, okay, you should be able to do it. All right. First part, if this is a distance versus time graph, it shows an acceleration and you're moving away. Here, okay, it is distance versus time. The distance is not moving, right? So it's standing still. This is constant speed coming towards you, getting to the origin, passing through the origin, continuing, all at constant speed. Here, stopped. And then here, you're going back towards the origin. So if we had little Jimmy on his tricycle, let's say little Jimmy's on his tricycle and he decides to leave his house and he starts coasting down the hill and he's going so fast that he ends up hitting a parked car. Boom. So he hits the parked car. He's sitting there. He's all dazed and confused. And then all of a sudden he hears, oh my God, Mr. Softy, Mr. Softy. And Mr. Softy's behind his house. So he gets on his bike and he goes back at constant speed as fast as he can, past his house to Mr. Softy, gets to Mr. Softy. All right. He orders, so he's not moving. And then he goes back home to eat his ice cream.